Swayam Prabha, free DTH channel for education.
We have written something like summation n equal to 1 to infinity an cos nx plus bn sin nx, okay, and then a naught plus we have written, and then we have written what are the a naught, an and bn. So this we have written, this is a series which is going to converge, okay, uniform convergence expression will be there, so that you can just define that f of x equal to a naught plus summation n equal to 1 to infinity an cos nx plus bn sin nx, you can write it. Now we are going to extend this idea, okay, we are going to generalize this idea, we are going to have two kinds of extensions we are going to have. So the idea behind the Fourier series we have seen is that the cos nx and sin nx, okay, the cos nx series and sin nx series here, okay, so here we had they are orthogonal system, okay, so that is one idea. So we had the idea of this is a orthogonal system, okay, sin nx and trigonometric system, sin nx and cos nx, they are forming an orthogonal system. So we exploited that property and then we constructed this one. So now first question I'm going to ask is that, okay, can we extend this, since trigonometry functions are orthogonal system, we use this. The question is, suppose I have some other orthogonal system, not only this sin x and cos x, suppose some other orthogonal system is there. So in that case, can we obtain a similar kind of formula? Okay, that is first question number one. Question number two, I'm going to ask this, whatever we have obtained so far is that f of x is periodic, we have obtained. Either it is a period 2 pi for cos nx and sin nx we have written, or if it is a period of 2l, then we change this to cos n pi by lx, sin n pi by lx, that we have obtained. Now suppose I have a function which is non-periodic, okay, non-periodic function. Can we extend this for a non-periodic general function? That is second question. Okay, non-periodic functions, that is second question. So first question is this one, second question is this one. So let us answer the second question first, okay. So let us try to ask this question, then let us answer the second question first. So the second question is, we are going to answer now. So just a recap. So this is the Fourier series which we have already specified in the last class and derived that, okay, and then we have solved some problems also. So f of x equal to a naught plus summation n equal to 1 to infinity. So this is the Fourier series which we have seen, which is given here. Now what we did, then period 2l also we have done, that is nothing but cos n pi by lx and sin n pi by lx we replaced, okay, with the sin nx and cos nx. So same thing, similar formula we obtained for a naught, an and bn. Then also we obtained the cosine series. Suppose if it's a even function, then one is going to vanish, okay, so if it's an even function, then sin term is going to vanish, only cos term is going to survive. If it's an odd function, cos term is going to vanish, only sin term is going to exist. So in that case we obtained two different series. One is Fourier cosine series, another is Fourier sine series. Now we are going to ask that question, okay. The question is, can we extend the method of Fourier series to a non-periodic function? So far we have did that for periodic function only. Can we extend this method for the non-periodic function? That's the question. The answer to this question is affirmative, means the concept is we can develop that. That concept is called Fourier integral, okay. That is the concept called Fourier integral. The idea behind that Fourier integral is that, suppose you have a function, okay, suppose you have a function, what I am going to find is that I am going to find a function fl, okay, I am going to find a function fl. This fl is going to be a periodic function, okay, I am going to construct a function, periodic function, okay. So fl is a periodic function. I am going to approximate this fx, or I am going to take, consider, okay, limit L tends to infinity fl of x, okay. So I am going to construct my fx is going to satisfy this one, f of x equal to limit L tends to infinity fl of x. So in that case, what you can say is that you can extend this idea, okay. That is the basic idea behind this Fourier integral. We are going to define a periodic function with period 2l, then we are allowing L tends to infinity, then that is going to give me the answer as f of x. If that is going to happen, then affirmatively you can answer that, you can get the answer. That's what we are going to do. Since FL is a periodic function, I can write this as, okay, I'm going to write FL of x, I'm going to write FL of x equal to a naught plus summation a cos x plus b and sin x is equal to zero. Okay, so now I'm going to take this period L, therefore here I'm going to take n pi by Lx I got to take. So that place I'm going to replace it as like omega nx, and here also I'm going to replace it as omega nx. Okay, so these two places I have replaced as omega nx. Where omega n is nothing but n pi by U. Now what we are going to do, okay, I'm going to substitute the values of an and bn over there. Okay, let me substitute the values of a and bn here. In that case, what we are going to get? So you are going to get something 1 by 2l summation minus L to L f of x f of L, okay, f of L into d dv plus summation. This is integral. This is summation n equal to 1 to infinity. An I know. An is nothing but cos plus cos w and x. And then I'm going to put the value of an. An is nothing but minus again 1 by L. Okay, 1 by L minus L to L. Okay, and then you got to obtain the value which is nothing but you got to multiply with cos function, and then you will get that FL of v cos omega n v dv. Okay, since there is a x already, I'm just making it as another variable. Okay, this is a dummy variable, so inside the integral this dummy variable. So plus I have same thing. Okay, plus I have similar thing sin omega n x 1 by L minus L to L FL of v sin omega n v dv is going to come. That's what I have. Now what I'm going to do, I'm going to write this as follows. A and b and I just substituted. I didn't do any magic. I just substituted the values of a and b. Now what I'm going to take is that I'm going to take a delta w. Okay, delta w. What I'm going to take is new. I'm going to introduce. Okay, omega n plus 1 minus omega n. I'm going to introduce. Okay, delta w is going to be omega n plus 1 minus omega n. So omega n is nothing but n pi by l. Therefore, this is going to become like n plus 1 pi by l. Okay, n plus 1 into pi by l minus n pi by l. Therefore, this is going to become like pi by l. N pi by l get cancelled. So you are going to get pi by l. So now what I am going to do is that I am just going to take this 1 by l. Okay, where I am going to replace it like pi by l. I am going to replace it. Okay, I'm going to replace that 1 by l wherever I have. So that place I'm going to write that 1 by l as delta w by. So this is going to be like 1 by l is going to be like 1 by pi into delta w is going to be. So wherever 1 by l is there, I'm going to replace this with delta w by pi. Okay, delta w by pi. Here also I'm going to replace it delta w by pi. Okay. Now what I am going to do, I am going to allow this, assume that, so the assumption we have already made, so we have that f is nothing but, f is going to take this one, f of x equal to limit L tends to infinity, FL of x is there, this assumption we have, okay. So if that is existing, okay, this is going to exist. If it is existing, then what we can do is that, we can allow delta w tends to 0, okay. If L tends to infinity, then automatically this delta w tends to 0, because L tends to infinity means delta w is going to be 1 by L. Okay, 1 by L is the delta w by pi is going to be 1 by L. Therefore, this is going to tends to 0. So this infinite series. So that means what it is going to come. If delta w is going to tends to 0, whatever I have here, okay, this summation, okay, you know the relation between the summation and integral is that suppose you are taking discrete sum, you are going to get n equal to 1 to infinity. If you are having a continuous thing, okay, instead of discrete thing, if you have a continuous thing, in that case we have that yes. Okay, this is even if you know the history of integral, that is the same thing. It is summation only. Okay, the summation. This is a prolonged sum. That is the reason it is having the shape of yes. Okay, the integral symbol is also having that history. So the summation, what I am going to do is that I am going to replace with integral. Therefore, this is going to become like okay, wherever I have that summation, that I am going to replace it from integral. So here it is going to take care of this one also. Okay, this part is also going to be taken care. This part is also going to be taken care because I'm going to replace n equal to 0 to infinity. Okay, n equal to 0 to infinity. Therefore, this is going to integral is going to become like instead of this one, it is going to be like 0 to infinity. So I'm going to replace this one. So in this case, what is it going to happen? I'm going to replace that. Okay, this is going to become like wherever I have, this is going to be taken care inside that. Okay, because I'm going to put 0 to infinity. So this is going to become like 0 to infinity, and this is going to become like, I'm going to take it as omega. Okay, omega n. I'm going to replace it as omega x. Okay, and again here, this is going to become like omega x, and this delta w is going to be like since you are having delta w. Okay, so this is going to become like small one. That is the reason it is becoming like a integral, summation becomes an integral. Okay, it's because of the delta w tends to 0 only, we are going to get this one. So therefore this is going to be taken care. Okay, so this is the one I'm going to have. So this integral is for both. Okay, or I can write this as 0 to infinity here also, not a problem. Okay, so 0 to infinity cos wx FLV cos omega n v dx. So now what I'm going to do is that I'm going to rewrite this equation as follows. Okay, I'm going to call so this L tends to infinity, then only delta W tends to 0. Therefore, this is going to become like minus infinity to plus infinity. Okay, and this is also going to become like minus infinity to plus infinity. Now, what I'm going to take, I'm going to call this one. Okay, and here also omega n will become omega. Okay, because of our delta W tends to 0. Okay, I'm just replacing it's a continuous one. So therefore, this is going to become like, okay, also this SL, I'm allowing a delta L tends to infinity. Therefore, this FL is also going to become like F of U. Okay, this is also going to become like F of U. So these are the changes going to happen when you are moving from the discrete sum to continuum hypothesis. Okay, this is a discrete one. This is a continuum one. Therefore, this is going to have a similar kind of thing where you are going to allow that delta W tends to 0 and L tends to infinity. So now this one I'm going to call it as A of W, and this one, okay, this one I'm going to call it as B of W. Therefore, this can be written as 1 by pi, okay, or even 1 by pi also I will take it inside that. So this one, therefore I can write f of x equal to integral 0 to infinity, okay, integral 0 to infinity A of W. So this is A of W, 1 by pi into this one is going to be A of W into cos omega x plus B of W into sin omega x. So B of W is this one together with 1 by pi. Okay, that is called the B of W. So this is the technique which we use for finding this is the integral is respect to TW. Okay, so this is the technique we use it for finding the Fourier integral. Okay, so from this theory only the Fourier transformation etc. came to the picture, and there you use this Fourier transform. After that, the fast Fourier transform, discrete Fourier transform, etc. came to the picture, and then you have many more applications of it in the electrical engineering and mechanical, geotechnical engineering, probably some mechanical engineering also. Because once we are using this one. This is the idea. This is the integral, this Fourier integral, or the Fourier series is the only one. We are going to use it for separation of variable in the heat equation and wave equation solution. We are going to use this concept. Okay, so that is the Fourier integral. Now, if it is again the same concept, suppose if it is an odd function, okay, then you are going to get one is going to vanish. If is even function, another is going to vanish. So if is an even function, then this is going to exist. Okay, cos omega is going to exist. This is going to vanish because even into r, therefore it is going to become like r minus infinity to infinity, therefore it is going to vanish. Similarly, if I have f is an odd function, this is going to survive because r into r is going to become even, whereas r into even is going to become like r, therefore this is going to vanish, this is going to survive. So in that case, we are going to get once again Fourier sine integral and Fourier cosine integral. Okay. So this is the idea. Then we have next one. Okay. Now next one, first question we answered. Okay, the question number 1 is that we asked a question. Actually, second question here. Okay, second question we asked is whether we can extend it for a non-periodic function. Yes, we have extended. That is called the Fourier integral. Now let us answer the first question. The first question is: suppose I found some other system, some other orthogonal system. Okay, can we extend this Fourier series idea further? Okay, that is second question. The answer for that is also affirmative. Okay, means we are going to get the answer as positively. So it is going to be yes. So the idea of Fourier series was to represent general periodic terms, periodic function in terms of sine and cosine. we enjoyed that. Okay, trigonometric systems enjoys the orthogonality and orthonormality property. So because of that, we got that series, Fourier series. Now, can we extend this to idea to any orthonormal system or any orthogonal system? Okay, any other orthogonal or orthonormal system? That is the question we are going to ask. The answer is again affirmative. Okay. So, for example, you can get a Fourier Legendre series and Fourier Bessel series, which we will see in this class. Okay. So, what I have, we have a problem called Sturm-Liouville problem. For this, we are going to use the concept called Sturm-Liouville problem. So, the Sturm-Liouville problem is going to say this is called Sturm-Liouville problem. Okay, y dash plus q of x plus r of x, lambda into r of x. Okay. Lambda into r of x into y equal to 0. Okay, with the boundary condition. Okay, the boundary conditions are k1. So it is defined on the interval. Let's say a comma b. Okay, a to b. It is defined in the interval a to b. Okay, a comma b. So I'm going to define the boundary condition also. K1 of y of a plus k2 of y of a equal to y dash of a. Y dash of a equal to 0. And k1 of let me put some other symbol. So L1 of, okay, let me put L1 of y of b plus L2 of y of b, y dash of b equal to 0. Okay, so this system is called Sturm-Liouville system. Okay, this boundary condition. So this is the boundary value problem. So this problem is called Sturm-Liouville problem. This equation is called Sturm-Liouville equation. This together is called Sturm-Liouville problem. Okay, now this is going to help us to solve some answer this question. Okay, this is going to help us to answer this question. Let us see. So for this problem, trivial solution is y equal to 0. Y equal to 0 is trivial solution because if I put y equal to 0, this is going to be satisfied. This is going to be satisfied. If I substitute here, this is going to become 0. This is going to become 0. So 0 equal to 0. If y equal to 0, then again here I am substituting. That way it is going to become 0. Now what we are going to do is that we are going to find whether there exists a non-trivial solution for this function. Okay. So that is the question we are going to ask. So then in this case, this is going to call it as eigenvalue problem. This is becoming like an eigenvalue problem. What we need to find is that we need to find a function y such that this is going to be satisfied. This would be non-trivial solution. For each lambda, you are going to get that. Okay, for each lambda, you are going to get that. So I can even call this as y lambda because this is associated with that eigenvalue. And if such a system is going to exist, okay, if such a function is going to exist, then I call this function as eigen function. Okay, this function is called eigen function. Okay, so let us take a quick look at this example 1, and then we will see, because please have more attention over here, because this is the one we are going to use it again and again in the PDE problem. Okay, so I'm going to answer that. So the problem is y double dash plus lambda y equal to 0. Okay, and then y of 0 equal to 0, y of pi equal to 0. This is a problem given. Now what we need to do is that you need to find the solution for this problem. Okay, so the solution is, you can simply say that there are many possibilities. Lambda is a real number. Okay, lambda belongs to that. There are many possibilities. So first case, let us take lambda is lambda equal to 0. Okay, simple case. If lambda equal to 0, okay, then this is going to become like y double dash equal to 0 is going to come. Okay, therefore y equal to y dash is going to become like a, and y equal to become ax plus b, where a and b are constant. Okay, so y equal to ax plus b. Now this is case 1. Okay, case 1 is lambda equal to 0. Then I substitute this. This would satisfy the boundary condition also. So y of 0 equal to 0 implies, okay, b equal to 0, because a into 0 plus b, therefore b equal to 0. Now y of pi equal to 0 implies a pi, already b is 0. Okay, therefore a pi equal to 0. Therefore pi is not equal to, therefore a equal to 0. That means I am going to have y is identically 0. Okay, but I am not interested in this one because it's a trivial solution. I am not interested in that. Case 2, I am going to consider lambda equal to some new square. Okay, some positive number of unity. Okay, so lambda equal to new square. That new is any real number. Okay, lambda equal to new square. Therefore, it is a positive number. Then what I am going to have, this is going to become like y double dash plus lambda y equal to 0. Okay, therefore y equal to the auxiliary equation you can find. The auxiliary equation is, I can write that auxiliary equation because this is new square, so I treat it as like new square. Therefore, the auxiliary equation is m square plus new square equal to 0. Okay, therefore m is going to become like okay. Case 2 will deal with that. Plus, okay, let's deal the other one. One sec. I'll just deal this case. Lambda equal to minus mu square. Okay, let's deal the lambda equal to minus mu square case first, and then we'll go for lambda equal to mu square case. So this case it is going to become like lambda double dash minus mu square into y equal to 0 is going to come. Therefore, auxiliary equation is m square minus lambda square equal to 0. Therefore, m equal to plus or minus mu is going to come. Okay. Therefore, my solution is going to become like y equal to a into e power mu x minus mu x is going to come. Now substitute that. Okay, y of 0 is going to become like a plus b equal to 0. Okay, therefore which implies a equal to minus b. Okay, and y of pi is equal to Did you listen up to case 1?
Yes, sir.
Yes, sir.
Okay. Okay, case 1 y equal to 0. Okay. Case 2 what I am going to take is that case 2 I am going to take lambda equal to minus mu square. Y double dash. Okay, this is going to be y double dash minus lambda square y equal to 0. Then m square minus mu square equal to 0 is there. M equal to plus or minus mu is going to come. So I can write that y equal to a e power x plus b e power minus 2x. So in this case, what is going to come? I'm going to substitute that boundary condition. So y of 0 equal to 0 implies a plus b equal to 0 plus a equal to minus b. Y of pi equal to 0 means a e power pi nu plus b e power minus pi nu is going to come. So in this case, I'm going to take a out. Okay, a equal to minus b I'm substituting. Okay, so this is going to become like minus a e power minus b pi. So if I take a out, this is going to become like e power nu pi and e power minus b pi. This is going to be 0 only if this is going to become like 1. This is going to happen only if nu equal to 0, but that case already I got discussed. My nu is always positive here. Okay, so therefore this is going to be a non-negative, non-zero number. Okay, a nu pi minus a minus nu pi is going to be a non-zero number. So two numbers are there. Their product is 0. Therefore, one of them should be 0. This is a non-zero number. Therefore, a should be 0. Since a equal to 0, b is 0. Therefore, y equal to 0. Again, I am not interested in this case. So only case I am left with is that I have case 3. Case 3 is that this is the thing we are going to repeat again and again in the case of heat equation and wave equation also. So keep remembering this. So that case is lambda equal to nu square. The nu is positive number. Nu is any real number. Okay, nu is any real number. Take it. Okay. So in this case, once again we are going to get y double dash plus nu square y equal to 0. So the auxiliary equation is going to become like m square plus nu square equal to 0. Therefore, m equal to plus or minus nu a is going to come. Then you are going to get y equal to a cos nu x plus b sin nu x is going to come. Okay. Now again I got to apply this condition. So y of 0 equal to 0 means what I am going to have a y of 0. Okay, y of 0 equal to 0. Therefore I am going to have a cos nu x. Oh, sorry. So y of 0 equal to 0 implies okay a this is cos x a cos 0. Okay, a is going to be there. This is going to be 0. Therefore, a equal to 0 is going to come. Okay. So next one I have y of pi equal to 0. Y of pi equal to 0 means I am having only a 0. Therefore, this is going to vanish. Only I have b sin nu x equal to 0. Okay. So in this case, there are two possibilities. Either b equal to 0. If b equal to 0, already I have that solution. Okay, I am not worried about that. Now b sin x nu x equal to 0 means what is going to happen? Okay, when b sin nu x is equal to 0, when sin is going to 0. Okay, so this is going to become like sin nu pi. Okay, this is going to be sin nu pi. Now what I have, I can choose my nu in such a way that there are two possibilities. Either sin nu pi is going to become 0 or b equal to 0. If b equal to 0, I am not going to worry because this is going to make me entire y becomes 0. So sin nu pi can be 0. Yes, it can be 0. Other than that, nu equal to 0 also. Okay, so in that case, what I have, I can put nu equal to n. Okay, nu equal to n if I put, then automatically this is going to become like 0 because sin n pi is 0. Therefore, what I got is that I got a nu equal to n is a solution for eigenvalue for this problem. Okay, nu is not eigenvalue. Nu equal to n is going to satisfy. Therefore, lambda equal to nu square or equal to n square is going to be the solution going to satisfy this relation. Okay, if I put lambda equal to n square, that is going to become like a eigenvalue for this problem. and the eigen functions are, so I can write for each one I am going to get eigen function. So that I am going to call the sine nu x, or I can say sine nx. Okay, sine nu x or sine nx. That is going to give me the answer for this function. Okay. So once you are keeping y n is equal to sine nu x and nu equal to n, then this is going to satisfy that. Okay, you can verify that if you put sine nx over here, y equal to sine nx and lambda equal to n, lambda equal to n square. Okay, then it is going to satisfy that. So therefore, lambda equal to mu square is an eigenvalue. Okay, and y's are called eigen functions. So this is the one we are going to keep on repeating in the case of heat equation also. So keep remembering that. Okay, now what is the point here is that we have some kind of eigen functions or eigen values and eigen functions are there. Now we are going to use this concept to develop the extend the Fourier series for generalization. Okay, generalized Fourier series we call it. Okay, so before that, once again we ask this question whether we can extend this idea for other orthogonal system. Okay, so that is going to help. This is going to help us to answer that. And one more preliminary we will cover it. Okay, so in the last class we have discussed what is an orthogonal system. Okay, orthogonal system or orthogonal, two functions are said to be orthogonal. Then the inner product is going to be 0, which is nothing but the integral on the interval. Okay, let's say a to b, and then you multiply yn fx and gx into dx. If that becomes 0, then we say that it is orthogonal. Now there is another concept is that suppose y1, y2, yn, okay, y1, y2, etc. Are some eigen functions, or even have some functions. Okay, some functions are right now. Forget about eigen function. We are going to extend that for eigen functions. Suppose y1, y2, etc. are eigen some functions. Okay, so that these functions are satisfying this relation. Okay, I am just having ym comma yn equal to integral a to b. This is defined on an interval. Okay, our functions defined on an interval a comma b. I am going to write ym comma yn integral a to b r of x into ym of x into yn of x into dx. Okay, if this becomes 0, then we say that ym and yn are orthogonal with respect to the function r of x, where r of x is called the weight function. Okay, this is called the weight function. So with respect to this weight function, they are going to become 0. So if we see the simple orthogonal, then r of x equal to 1 we can take. That is nothing but your orthogonal. If you want to say orthogonal, then you can simply take r of x equal to 1. That means it is orthogonal function with respect to 1, with respect to the weight function. Now if it is the orthonormal, then what I am going to define is that ym comma yn equal to, okay, ym comma yn equal to 0 if m is not equal to n. Okay, 1 if m is equal to n. Okay, so in that case I say that if m equal to n, I say that this is m equal to n, it becomes 1, m not equal to 1, it becomes 0. That we call it as orthonormal. Again, the same definition with respect to weight function r only. Okay, with respect to the weight function r. So I put rx equal to 1, then we simply call it as orthonormal. So that we have seen already. Okay, so orthogonal function. So if r of x equal to 1, we simply say it is orthogonal. We don't say it is orthogonal with respect to the function. We simply say orthogonal. Okay, already we have seen some examples like the trigonometric system is orthogonal in the interval. Okay, which we have seen with respect to the function r of x equal to 1. Now you can verify that this is called Chebyshev polynomials. Okay, Chebyshev polynomials of second kind. The Chebyshev polynomials of second kinds are again orthogonal. You can verify that. So you can just multiply with the square root of 1 minus x square and take any two functions over there. Okay, from y0 to y5, take any two functions. Okay, and calculate the integration. That is going to become like 0 in the interval minus 1 comma 1. Okay, that is again orthogonal with respect to the function y equal to rx equal to root of 1 minus x square. You got to multiply with the root of 1 minus x square and then multiply with 1 and take 2x here. Then you can check verify that is going to become 0. Similarly, you can take the other things, that is going to become 0. Okay. Okay. Now next one, legendary equation. Okay. So we have seen that our Sturm-Liouville problem. Okay, the Sturm-Liouville problem we have Sturm-Liouville problem we have something like p of x into y dash of dash plus q of x plus lambda into r of x into y equal to 0 was there. This is the Sturm-Liouville problem, and then we have the boundary conditions, etc. Okay, so this is the Sturm-Liouville equation. Now we are going to see whether our Legendre polynomial is a Sturm-Liouville problem. So our Legendre polynomial is 1 minus x square y double dash plus minus 2x y dash, okay, minus 2x y dash plus n into n plus 1 y equal to 0. Okay, this is our Sturm-Liouville problem. So I can, so this is the Legendre equation. Now I can write this as 1 minus x square y dash the whole dash, okay, plus n into n plus 1 y equal to 0. So here you can see that p of x is nothing but 1 minus x square. Okay, q is 0 here, and lambda is going to be n into n plus 1, n into n plus 1, okay, and r is going to be 1. Okay, so you can just check that this is a Sturm-Liouville problem. Okay, so the Legendre polynomials also we have seen this one the 2 classes before. We verified that pm into pm, okay, into dx equal to 0 minus 1 to 1, 0 if m not equal to n, okay, and then 2n plus 1, 2 by 2n plus 1, okay, 2 by 2n plus 1 if m equal to n. This we have seen, okay, 2 classes before we have seen that. So therefore this is a orthogonal system. So we already said that we are going to extend this for the Fourier series. Okay, now we are going to extend that. So in this case, what I can do is that, okay, this is the Sturm-Liouville problem. So we extend that for the generalized Fourier series for the moment. Let's keep it. Similarly, let's keep this one, and we are going to extend that further. Similarly, I can do the same thing for our Bessel series. Okay, that is the Bessel equation. So x square y double dash, okay, plus xy dash. I'm going to write some parameterized Bessel equation. So parameterized Bessel equation means I'm just putting some lambda here, lambda square x square minus let's say n square, okay, n square y. So usually we mentioned x square minus n square y equal to 0 we mentioned. Now here we are mentioning lambda square x square dmt. This is called parameterized Bessel equation. So in this case, once again I can write this as xy dash the whole dash, okay, plus I can write this as lambda square, okay, x minus n square by x into y. This is equal to 0. So in this case, I can take p of x equal to x and q of x equal to minus n square by x. Okay, q of x equal to minus n square by x and r of x equal to x. Then in this case, this is once again becoming like a eigenvalue Sturm-Liouville problem. Okay, this is once again Sturm-Liouville problem. So in this case, once again, what we can do is that we can find the similar kind of system. Okay, so that system is I have something called, this is Bessel series is Bessel functions or Bessel series of first kind is orthogonal with respect to the right function x. Okay, so this we are going to write lambda n in jn is the Bessel series. Okay, jn lambda x into jm nu x. Okay, where lambda and nu are here, lambda and nu are roots of the equation jn of x. Roots of the equation jn of x. Okay, so this is the roots of this one. So this is going to become 0 if lambda not equal to nu. Okay, and then 1 by 2 jn plus 1 whole square of lambda. Okay, if lambda equal to nu. Okay, so this is once again orthonormal system. Okay, which you can just think of it. Okay, maybe I will ask this question in one of the exam. So you can just verify that. Okay, x into jn of lambda x plus jn into v of x is going to become like this. Okay, so as I keep jn only. Okay. Okay. Now we are going to extend this idea for our orthogonalized generalized Fourier series. Let's see that. Okay, one more is that. So this is also Chebyshev's differential equation. Okay, I will write it here. So Chebyshev's differential equation is 1 minus x square y double dash, okay, minus xy dash plus n square y equal to 0. This is called Chebyshev's differential. This is something similar to what we discussed in the Legendre equation and Bessel equation. This is called Chebyshev's differential equation. So here, this is once again you can say that you are going to get a similar kind of thing. You can this can be written as square root of 1 minus x square y dash hold as, okay, plus n square to the square root of 1 minus x square. You can verify that this is going to satisfy the Sturm Liouville problem, where p is square root of 1 minus x square and r is 1 by square root of 1 minus x square. Q is going to become 0. Okay, you can verify that. So this is going to be the case for Sturm Liouville because in 3 problems. Now we are going to go for the generalized Fourier series. So what we are going to do is that suppose we have a orthogonal functions. Not orthogonal, orthogonal functions. y0, y1, etc., y2, etc. is that. This is an orthogonal system. Is that. Okay. For this orthogonal system, can we extend this idea for a Fourier series? Okay, this is orthogonal with respect to the weight function r of x. So in this case, can we extend this idea? Yes, we can. So any function f can be represented by a convergent series of this kind. So f of x equal to summation n equal to 0 to infinity an into yn of x. Okay, this an can be found as we did in the earlier case. Okay, this is called as we did in the earlier case. This an persons can be found. Okay, we will see that. So this series is called generalized Fourier series. Okay, if yns are sin x and cos x, then this is going to be like a simple Fourier series. If yns are other than that sin x and cos x, and you found an orthogonal system, then this is called generalized Fourier series. Okay, and this is also called as orthogonal series because you are taking everything as orthogonal system. You are taking it from an orthogonal system. Therefore, this is called an orthogonal series, or also it is called as an orthogonal expansion or generalized orthogonal series. Okay, these are the names for it. And here, these yns are called if the yns are eigen functions of this Sturm Liouville problem. Okay, if it is these yns are obtained from this eigenvalue problem, then in that case, this is also called as eigen function expansion. Okay, this problem is this is also called as eigen function expansion. Okay, this generalized. So let us see some of the examples also. So how do we find this an? Okay, the same technique what we used over there. You multiply this one. Okay, you multiply this one with yn and multiply here with yn and integrate this integrate with respect to the r of x. Okay, sorry, multiply with r of x into yn. Okay, then this is going to become like r of x into yn of x into f of x dx is going to come. Here, for example, I can just do that. So if I multiply here, this is going to become like r of x into yn of x into f of x is going to come into dx. On the right hand side, okay, this since it is an orthogonal function, except n equal except n, everything is going to become 0. Okay, if I take m value here, this is going to become 0. Except m equal to n, it is going to be surviving. Okay, so remaining all going to become 0. So in that case, you are going to get an into some term is going to come. That term is going to be identified by the integration of yn with yn, because that is not orthogonal means only yn not equal to m is going to vanish, otherwise it is going to survive. So only those terms is going to survive. So that one I am going to divide it over here. That is nothing but again integral a to b r of x into yn square x is going to come. Okay, this is going to become like even I can write that. So this is going to survive only that term. That is going to become like r of x into yn square of x into dx is going to survive. Therefore, an is going to become like this integral a to b. Okay, integral a to b r of x yn of x f of x dx, and you can divide it. Okay, so this is the way you can find the an for the generalized series. So let us see a simple problem. Okay, I'm not going to solve that. I'm just going to give the idea. Suppose here, in this case, what I can do is that this is the orthogonal function. Therefore, I can obtain the orthogonal generalized Fourier series for this one, and that is called Fourier Legendre series because I'm using a Legendre polynomial here, and Legendre polynomials are orthogonal. Therefore, this is called Fourier Legendre series. So in this case, I can write f of x equal to summation an pn of x d pn of x. That's all. Okay, so this is called Legendre Fourier Legendre series, where an can be found in this way. Okay, an can be found in this way. 2n plus 1 by 2 into f of x into pn of x dx. You can write it. Okay, then you are going to get the answer for it. So the denominator is going to become vanishing because you are not going to have. So this is going to become like pn square of x into pn square of x is going to become like you are going to get this one. 2 by 2n plus 1 is going to come. Okay, integral pn square. So this is with respect to the r of x equal to 1 case. Okay, so in this case you are going to get f of x into pn of x is going to come. 2n square of x is going to become like 2 by 2n plus 1. So if I take over here, then this is going to become like 2n plus 1 by 2 is square. So therefore that is nothing but my an is square. So I have given an f of x, like the way you do for the Fourier series, you can do the same thing for Fourier legendary series also. Okay, same thing you can do that. This is an exercise. Now we can extend this for the Bessel series also. So in the case of Bessel series here, again this is an orthogonal function with respect to the r of x equal to x. Therefore, what I can do, I can write this also the same way: f of x equal to summation n equal to 0 to infinity. Okay, or I got written m over that doesn't matter. So an into j. Okay, so there I have used that because that is corresponding to the roots of the equation. That's the reason I got written, because that's corresponding to that. Okay, so an, instead of that I'm going to put am jn of alpha m. Okay, alpha m's are called the roots of this jn of x. Okay, alpha m of x. Okay, so this is going to give me the Fourier Bessel series, where am can be found in this way. Okay, am can be found in this way. Once again, do the same thing. Multiply this with x and jm of alpha mx. Therefore, everything is going to vanish except that jm equal to lambda equal to nu case. Means alpha m equal to m equal to n case is going away, otherwise it is going to vanish. So in that case, once again you are going to get this one. Okay, so that is the reason I am keeping the jn plus 1 alpha m a is going to come. Now this is integral over 0 t. We got to do that integral over 0 t here. Okay, so that is the Fourier Bessel series. So again, I have given an example, the exercise which you can do. Next one. Okay, that's all. Okay. Okay. So this is up to, this is for the case of, we consider the Fourier series, where we have considered, initially we considered the orthogonal system, periodic function we have taken, and then we extend that periodic functions to we expanded the properties of the trigonometric system, and that is enjoying the properties of orthogonality and orthonormality, and we used that idea to develop a series called Fourier series. Okay, and from that we have obtained that non-periodic function also we have expanded, and then we asked another question: some other orthogonal system can we do that? That also we asked. Okay, so with this our ODE part is almost complete. The ODE part and series is complete, but again we are going to use a similar kind of concept for our partial differential equation also, because once you are solving the partial differential equation, once again you are going to transform that to a known domain. That known domain is once again the differential equation, ordinary differential equation. So we'll use some set of assumptions. Using that assumption, what you are going to do is that you are going to get once again the same kind of differential equation, ordinary differential equation, and then you are going to solve. So let us have a quick look about the partial differential equation. So this one we have already seen partial derivatives, which I have explained in the first or second class. So in the partial derivatives, what we have is that what is the derivative we have already seen. So in the partial derivative means your function should be at least defined at 2 variables. Minimum 2 variables should be there. So in that case, you are going to get, if it is a function of one variable, then you are going to get a curve. Okay, if it is a function of one variable, you are going to get a curve. If it is a function of at least 2 variables, then you are going to get something like a surface is going to. Okay, it is going to become a 3-dimensional. Therefore, you are going to get a surface like this. The gray color one is a surface. Okay, so you are going to get a surface over. So for that surface, what I am going to do is that I am going to find what is the partial derivative. So in this case, I am going to take a plane y equal to b. Okay, for example, y equal to b. I am going to take a big knife and then cut it over there. If I cut it over there, it is going to intersect that surface. That surface is going to form a, that intersection is going to form a curve. Now for that curve, I can find the tangent. Okay, that is going to come from the differential equation, the different derivative, ordinary derivatives. Okay, the derivative. So that is going to call us the, from that we are going to obtain the partial derivative. So this one we have already seen in the last first or second lecture. So I'm just quickly wrapping it up. So the partial derivative with respect to x at the point a comma b, we define that fx at a comma b equal to dou f by dou x at a comma b, which is nothing but we are fixing the variable b. Okay, so df by dx, which is nothing but you can see that dou f by dou x at a comma b is becoming like df by dx. That means it's an ordinary derivative. Okay, ordinary derivative you are taking. So df b is fixed, therefore only x is going to change. So that one I got to evaluate at x equal to a. Then we are applying the concept of derivative concept, which is going to become like limit h tends to a. f of a plus h comma b minus f of a comma b by h is going to. Okay, fine. Now this one also we have seen, and last in the first or second lecture we asked this question. So suppose u equal to e power x minus y, then we know that ux plus uy equal to 0. Okay, you can just verify that. This we got it already, and we asked this question whether u equal to e power x minus y is going to come. Similarly, ux plus uy equal to 2u is going to come. Then we ask this question whether u equal to e power x minus y is going to come. The answer is not unique. Okay, will you get a unique answer? The answer is no. Okay, so for example, if I take ux plus uy equal to 0, then you are going to get u equal to f of x minus y. Okay, you can verify that. So quickly let's see. So u equal to ux plus uy equal to 0. Okay, and if you take u equal to f of x minus y, this is called a transport equation, we used to say. Okay, so this is going to become like ux, if you take this is going to become like f dash of x minus y into 1. Okay, y is going to become like minus f dash of x minus y, because I have to differentiate with respect to y as I have used the chain rule. So this is going to be that. So if I sum it up together, this is going to become 0. So it is not necessary that in general u equal to e power x minus y is only the answer. You can take any of these. Similarly, we have ux plus uy equal to 2u is called the Helmholtz equation. In that case, also once again you will get the similar kind of thing. So in that case, we cannot guarantee that only one solution is going to come. Many solutions will come. Now we are going to do. We are going to see some history of this partial derivative, how it came to the pictures, etc. So this was first used in 1694 by Liouville. He used the partial process. He didn't say it is a partial derivative or something, but once he was developing some kind of mass relations, etc., he did that the mass is changing with respect to one variable, then it is going to change with other variable, etc. So in that case, he used this concept called partial process. Okay, so partial process, which is not explicitly del m, but dou m by he used like a del m. Okay, instead of dou m by dou x, he used del m. And this dou m by dou y was developed by the letter to d elasticity. Okay, the letter due to elasticity. Okay, a letter due to elasticity. So 1694 again Liouville used the partial differential equation to find the envelope of circle. So envelope, for finding the envelope of a circle, he used this one. Means he differentiated this one. First he kept y equal to constant and then differentiated, and then he kept x's constant and then differentiated, and then he found what is the envelope of a circle from this. Then 1717 Fermat used PDE problems of orthogonal trajectories to plane curves. In 1752 D'Alembert introduced one-dimensional wave equation as a model of vibrating string. So that we have already seen in the second lecture how to obtain the wave equation. So that is nothing but you take a violin string and then see the disturbance, etc. and then you do it. Okay. So that was obtained by D'Alembert in time one-dimensional wave equation he obtained, which is for vibrating string. And then 1759 Euler extended the D'Alembert string. He extended this further for further the wave equation to other dimensions. Then D. Bernoulli extended this to second and third dimensional wave equation. Okay. Then 1780 Laplace studied about the gravitational potential fields, which is one of the important concept in the geotechnical engineering and electrical engineering. Okay, that was studied by Laplace. He used that gravitational potential field. Also, it is used in the mechanical engineering also in some scenarios. So that this gravitational potential fields are playing. Then Euler equation of compressible flows was developed in 1755, and there is a minimal surface equation, which is one of the key concept in nowadays in the missile landing, etc. So that is by 1760 by Lagrange, and then Monge-Ampere equation by Monge in 1775, and Poisson equation, which is one of the important equation that was developed in 1830. Okay. And then Green was working on the Green's functions, etc. Gauss was working some other similar to that in the equations. Then this is one of the major contribution. Navier and Stokes, these two scientists, they developed the equation called Navier-Stokes equation, that is governing the fluid flows, okay, which is one of the most important problem in the mechanical engineering, especially the computational fluid dynamics whoever is working. In that case, or even if you work on thermodynamics also, okay, so in that case you are going to deal with this Navier-Stokes equation somehow, or even if you see the how the weather is predicted, etc., that is also part of this is going to. Okay, and if you take the tsunami equation, means tsunami waves, or cellular water equation. So that is called cellular water equation. So those are all again the derivation from this Navier-Stokes equation. And this is Navier-Stokes equation finding the solution, because right now we are checking whether you have a unique solution or not. So those things we are developing. So in Navier-Stokes equation, there is a $1 billion problem is there. Probably if you want to know more, you can just go to my website where I have given a lecture about different partial differential equation also. So in that case, you can see some of the lectures about the $1 million problem of this Navier-Stokes equation. Either you can see my YouTube video, or you can see the lecture notes which I have provided in the website. Okay, so that you can see. And then in 1821, linear velocity was studied by Navier, and Cauchy was studying the same thing in 1822. Maxwell's one of the most important equation in this 18th century, okay, which is still used in many of the applications. Okay, so that is one of the equation which is called Maxwell's equation. And then Helmholtz equation, again, it's another important equation, okay, in the physics environment as well as in the quantum physics, etc. So that is again the Helmholtz equation and eigenvalue problem for the Laplace operator that was developed in 1860. And then there is another problem called Plateau problem, which is used in some of the geotechnical engineering problems. 1840 was developed. And then Kortberg D-Virus equation was developed in 1896. Okay, so these are all the differential equations, partial differential equations development. Then how do they find the solutions? Okay, for solutions, the history of the solutions are, first thing is in D'Alembert, he solved the wave equation by method of separation of variable. So the method of separation of variable means, suppose you have an equation like this, what I am going to do is that I am going to assume that u can be separated like this. So I will say like x of x into y of 1. Okay, if I can write this one, then what I can do is that I can just substitute it over here. I can just obtain my x, u of x, because x is independent of y. Therefore, if I find u x, it is going to become like only x dash of x into y of y is going to come. Similarly, if I find u of y, this is going to become like x of x into y of y is going to come, and then substitute it over here, and then you can make some divisions, etc. Then you are going to get the answers. So that is the method which was developed in 1747, which we are going to use it. This is the only method we are going to solve in your course. Okay, there are other methods available. For that you can refer my partial differential equation course notes. Okay, so that there are many methods are available. So this is the only thing we are going to develop in this. We are going to work out only this one. Okay, we are going to assume this, and then we are going to work out on this one. And then we have so this is the developed by method of separation variable by D'Alembert in 1747, and this was extended by Euler in 1748. And again they worked on the wave equation only. And Laplace again used this in 1748, and Legendre used it for Laplace equation. Okay, Legendre for Laplace equation in 1811 to 1824, and okay, so then Fourier also used this for heat equation. Okay, 1811 to 1827, Fourier also used this for the heat equation. Then Fourier was the one who developed this Fourier series. Okay, with this concept of what we call that trigonometric systems, etc. Okay, so that one he developed an infinite series solution using this eigenvalue problems, etc. So that one lead to Fourier series and Fourier integral. And then other people like Riemann has used Riemann and analytic function, Riemann real harmonic and analytic functions. So this is another method which you can see it in my lectures, etc. So analytic functions also they have used, and that was from Riemann used, and then Neumann, Squarz, Christoffel, these people have used. Green's function, which we have seen for our ordinary differential equation, the same thing is available for the Laplace equation, and then you can extend it for the heat equation and wave equation also. That is done in 1835. Okay. Then Dirichlet principle, this was developed. That is another principle where we use the energy norm, etc., which is one of the key concepts for the finite element method, which most of the mechanical engineers is going to use it. So that is one of the key concepts for that. Okay, where you will use something similar to that, like Dirichlet principle. So that was developed by Green in 1833 and 1850, and by other people like. Then there was the power series method by Euler and D'Alembert and Laplace and others. They did that, and then they extend this idea for nonlinear PDEs also in 1840. And convergence of the power series to general system, that was done by Kowalski and Korstar. Okay, And the other questions like in existence of Dirichlet principle, integral question by Riemann. So there are 23 problems by Hilbert, known as Hilbert problems. So in that we are discussing about this existence, regularity, etc. Okay. Again, you can refer for most of the things. You can refer my lecture notes. Okay. And integral equations, which was done by Neumann in 1877, and then it was studied by Poincare and predominant derivatives are there, or kernels of that. Then in 1880, the Picard successive approximation was obtained. So that is one of the key idea for the uniqueness and existence theorem, which you have studied in the ordinary differential equation, first order ordinary differential equation, that can be extended for these cases also. Then Hilbert, Levy, Lebesgue, Rubini, Sarambla, Courant, these are all the people who are working on this, who worked in this 19th century. They worked on that. And other theories like Ascalier theorem, Sobolev spaces, peak solutions, distributions. These are all the things which you will be coming across once you are using the finite element methods or some of the numerical techniques like finite element method, finite volume method, etc. So in that case, you will be coming across. So these are all some of the techniques. So far, it is going on. Okay, spectral theories. Okay, so with this, I will stop that. I will start with the PDE preliminaries in the next class, and then I will give you the derivation of transport equation, especially the diffusion equation, which I will use it for developing. Like that is going to be helpful for some of the civil engineering students who is working on the air pollution. Okay, who is working on civil and environment engineering, where whoever is working on the pollution, air pollution projects or something similar to that. There you will see a similar kind of equation where you can see that. Also, there is a theory available. Okay, so I just want to say I will just show one more thing and then I will just stop it. So what is the thing is that I thought to show it in between, but I forgot. Okay, so this is about the Fourier series. Okay, the Fourier series, what I have is that this is working. Go. Fourier series. You can see it in my website at any time, but I'm just showing it so that at least you will see once in your life. So this is the Fourier series. Okay, where what we are doing is that we are just approximating that. Okay, you are having a function. This is my function. Okay, S6 of x is there. Then you are approximating using a n cos n x. So what is it going to do? You are taking. So it is going to show you how it is going to do. So you are taking sine curve, then sine 1x, sine 2x, sine 3x, something like that. Okay, the sine. Those one we are taking and then summing it up together. That summing up is going to give you the Fourier series. Okay, so this is the function which you are going to obtain from them. So you are going to have many sin x and cos x terms there that you are summing it up together and then you are going to get this answer. Okay, 6 of x. So this is the one thing I want to show. And other animations are there like Laplace equation, Poisson equation. This I have developed using the MATLAB functions. So which also you can check. Okay. And one more thing, yeah, I just want to show one more thing. Yeah, this is the one, the geotechnical engineering people may be interested. So that is called Tarasaki's one-dimensional consolidation theory. Okay, so that is once again the, not this one. Notes. Okay, so this is Tarasaki's one-dimensional consolidation theory. This is the one which you will be using for some of the geotechnical engineers will be using. So this is something similar to what we are going to use in the case of our wave equation, sorry, heat equation. Okay, UTC